A manufacturer of bolts knows from past experience that 50% of her products are defective. Use normal approximation to find the probability that a box of 100 of these bolts contains exactly 49 defective bolts. So they're telling us in the question to use normal approximation, but they didn't tell me a mean or a standard deviation or anything like that. So what are we to do? Well, think about how we would inspect these bolts. You'd pick up one of the 100 bolts in the box, and you'd check, is it defective or not? 2 outcomes, and you're doing this 100 times. What we have here is a binomial random variable. We're doing something 100 times, and the chance of finding a defective bolt is 0.5. So that means we've got a particular probability that we might like. And we want the probability in this question that out of a box of 100 we get exactly 49. Our binomial random variable counts the number of defective bolts, and we want exactly 49 of them. So that's what we're after here. That's what we want. Now you may remember from earlier when we've talked about binomial random variables that there actually is a formula based on what we've learned in section 2.7 for exactly this value. But even if you gave me a calculator, this would be a very hard thing for me to calculate. 100 choose 49 is a really big number. 0.5 to the 49, 0.5 to the 51, these are really small numbers. So they will balance each other out, and there will be a probability, but I have no idea what that would be. And it's not easy for me to calculate. And furthermore, if we look at the question, they specifically say use normal approximation, not the formula that you've learned in the past. Okay? But because this expression here is not easy to calculate, okay? This is not an easy formula to work with. It's an exact formula, but the value, I have no idea what the actual value as a number is not easy to work with. This is one of the reasons why we like normal approximation. We'll get close enough. We'll get an answer to 4 decimal places. Now, because we're working with a binomial random variable, we can find its mean, it's just n times p. So in this case, that'll be 50. And its standard deviation is the square root of n times p times 1 minus p. So square root of 100 times 0.5 times another 0.5. So that'll be the square root of 25. So in this case, our standard deviation is just 5. Okay? And we want this particular probability. What are we going to do? We're going to draw a mock histogram to start off to understand our binomial random variable. It's a discrete random variable. So we might put some boxes here. It doesn't have to be accurate. It just has to be a histogram for our purposes to understand what is shaded, where the area starts and where it stops. I'll probably put 50 in the middle here. And we're interested in just 49. So we want just this shaded box here. Okay? And what we're going to do is we're going to come along and approximate this with a normal distribution, a normal bell curve. And that'll smooth things out, and we'll have the same area, okay, more or less. And where does this area start, and where does it stop? Well, since we're counting the defective bolts, everything's going up by ones. So 48, 47, if we count this way, 51, 52, and so on. And so we can see the shaded area starts halfway between 48 and 49, and ends halfway between 49 and 50. So the probability in terms of the discrete random variable that we would like to calculate now becomes the probability in terms of, let's say, x, or well, to keep it more in line with what we learned in the lesson, we'll say y. And y here is just a good approximation that happens to be normal. And I might say, let y be normal with the same mean and standard deviation. Okay? Y is a good approximation, so we can make this trade. The probability we want for this probability in terms of y. And now it's not a question from 4.4, it's a 4.3 question. Okay? It's a probability in terms of a non-standard normal. And what we're going to do now is use sort of that x minus mu over sigma to change these values that we're comparing y to into z-scores that we can compare our standard normal to. Okay, so what do? Well, x minus mu over sigma, and the other one as well. And we have to simplify these, and then we'll have a probability in terms of the standard normal random variable that we can look up in the chart. So 48.5 minus 50 is negative 1.5. And we'll get negative 0.5 here. Negative 1.5, well, 15 over 5 would be 3, so we get negative 0.3. And 0.5 over 5 is 0.1, so we get negative 0.10. And now it's up to us to figure out this probability, which we can now break up into two different probabilities with one z-score apiece, as we've done in the past. Okay, that's up to us to work these probabilities out. Okay, so what do? Well, for the first one, draw our z, our standard normal distribution. Negative 0.1 is over here. We want the area to the left. Well, that's the same as if the area was over here on the right side. And we flipped everything and got a positive z-score. And that is 1 minus the area to the left. So we want 1 minus the probability z is less than 0.10. And that I can look up in our cumulative distribution table. So 0.10, we've got 0.5398. So 1 minus 0.5398, and we can go ahead and simplify that. We'll get a 2 here, a 0 here, a 6 here, and a 4 here. Okay, so that's the first value. Now we do the same thing, but with negative 0.3. Okay. In fact, it's going to be the same series of flips and everything, because we're still working with a negative z-score. Okay. The area is shaded to the left, and then when we flip it over to the other side so the z-score is positive, the area shifts to the right. And so we do 1 minus the area to the left, because the area to the left is something that we can handle. Okay, so we're really just applying everything we've learned. Mock histograms, good approximations, shading, flipping, symmetries, all of that fun stuff. So 1 minus, and now we look up for 0.3. Go one further. There we go. 0.6179. So this area is 1 minus 0.6179. So we'll get a 1, a 2, an 8, and a 3. Now what do we want? Just go back here and double check. We want the one minus the other. So 0.4602. We'll just go back to our original expression. So that's going to be 0.4602, right? 4602 minus 0.3821. And we'll just do it by hand over on the side here. 1 from 2 is 1. I'm going to have to borrow here, make 10. Borrow here, make 15. So the probability is about 0.0781. And if you actually were able to grab a calculator and evaluate this expression, the exact expression for the answer, you would find it's about this number. Right? They're particularly close. But this way, we've used our normal approximation. Drew a mock histogram, figured out where the areas started and stopped. We were able to switch to an actual normal curve, but it was non-standard, so we shifted around and then started answering and finding values for our standard normal.